let me post in the questions. That would actually be really helpful if I were to do that. Okay. So these are RAID questions. So we have a RAID 0 array with 4 disks. Each disk has a read-write speed of 100 megabytes per second. Calculate the theoretical maximum read-write speeds of a RAID 0 array. Explain why RAID 0 achieves these speeds. What is RAID 0? It's stripping, essentially. So if this is like A, B, C, D. This can read 100, this can read 100, this can read 100, this can read 100. How many can be read together? 400. I can read 100 from each of the 4 disks at the same time. And that's what's great about RAID 0. You're able to read from multiple disks at the same time. I can read from this disk and this disk and this disk and this disk from the same time. If this was like a mirror, I would only have like half the disks that were there. So stripping is actually very good. But it's not good when one of the disks goes down. If this disk goes down, good luck. You can't read anything else. So that would be the case for question 1. Question 2. You have a RAID 1 array with 4 disks, each of 500 gigabytes capacity. Okay, this one, the answer is wrong in the answer key. He said that the way we're treating RAID 1 is split it down the middle. These are mirrors. These are mirrors. Mirror, mirror. The way that they were treating it was one disk and everything else is a mirror of it. Whenever you're doing RAID 1, you're always going to have the same amount of mirrors as you are the actual data. It always must be even, and you can only have even numbers. So it has to be the same number. So 2, 2. You could have 6, 3, and 3, etc. Essentially, you're always going to have one user data disk for one mirrored disk. So I could also have like a CC. These are mirrors. This is the way we're treating mirroring. You could have more than that amount of mirrors if you want to. It's totally up to you. That also gets into like RAID 1.0, which there's a question here, I think. Yeah, let's just skip to 5 real quick because this deals with 1.0. So what is 1.0 saying? Well, the way to think of it is you do the 1 first, right? So there's 4 disks. And you're going to be doing a mirror here, a mirror here. So this is 1, this is 1. You start with the inside and then you go outside. These guys are joined together by a 0. So you can think of it this way. You're choosing to strip it into group A or group B for RAID 1.0. So you start with the first number, inside, second number, outside. Think Inside Out, like the movie. So you're essentially stripping it between the 2 inner groups. And these are a mirror of one another, and these are a mirror of one another. So that's a mirror, that's a mirror. And you're stripping it between, do I do group 1 or do I group 2? What's great about this is that if you have one disk that fails, if this disk fails, guess what? You have the info on this disk. If this disk fails, you have the info on this disk. If 2 disks fail, then you got a problem. That's why the fault tolerance of mirroring is usually up to 2 disks. If you have more than 2 disks, if you have 2 or more, then you're not able to get back your data. And that's also the answer to
I have
5.
a question.
Mhm.
If we had RAID 01, would it be AB, AB? Two clusters of AB, AB?
Yeah, exactly. So inside, out. 0, 0, 0, 0, and it's a mirror. A, B, because you're stripping it across this way, and A, B, you're stripping it across this way. And these are the mirrors of one another. So it's just a matter, what's on the inside, what's on the outside. So let's do parity real quick. Parity is actually pretty easy. Question 3. 4 disks, 3 disks, sorry, with RAID 4. This has a bit of 1, this has a bit of 0, this has a bit of 1. The parity bit is calculated with XOR. Find the parity bit value. Parity bit, if the amount of ones are even, it's 0. If the ones are odd, it's 1. How many ones are there? 2. It's even. Parity bit is 0. Likewise, question 4. Same thing. Disk 2 fails. 1, 2, 3, 4, 5. RAID 5, okay. This has a bit of 1, 0, 1. Oh, disk 2 was the one that failed. So we don't know what this one was. Disk 3 is 1, and our parity one is 0. Well, 0 is telling me the ones are even. How many ones do I have? 2. If I were to put a third one in, it would be odd. This has to be a 0 to keep the numbers of ones even. There's one more parity here. You kind of get the point at this point. 1, 1, 0, 0. The parity is 0 because these guys are even. So if one of these were missing, oh, it's 0, they have to be even, the ones. There's only 1, 1 here. I need a second one here to make it even. That's essentially what you're doing with parity. Now you could make a truth table with this too. Like if you were to say 1, 2, 0, 1, 1, 0, 0, 0, 1, 1. Right, these are the 4 cases. With a 0 and a 1, it's a 1. With a 1 and a 0, it's 1. Right, exclusive OR. It's exclusively OR, it's one or the other. 0 and 0 is 0 because there's no 1. And 1, 1, well, again, if this was regular OR, this would be true, technically, but because it's exclusive OR, I think exclusively OR, what you think of when you hear OR. Like, do you want a side of fries or a side of a salad? You pick one or the other. That's what exclusive OR is saying. So 1, 1, this is technically 0 as well. This is false because both of these are 1. It's not exclusively what we traditionally think of OR. This is the way of doing a truth table. I don't think he's going to ask a truth table, but if you wanted to understand how that works, yeah, parity ain't that bad. I was honestly really confused at this at first, but it's not too bad. And last question, I know I kind of went a little out of order, but the last question would be question 6. So this is another confusing one, right? RAID 60. So 2 RAID 6 sets, each with 4 disks. So think of it this way, 2 RAID 6, inside, outside, inside, outside, you're stripping them between these two groups. What do each of these groups have? 2 RAID 6 sets, each with 4 disks. 1, 2, 3, 4, 1, 2, 3, 4. And each disk is 2 terabytes. Yeah, so each of these are RAID 6. What is RAID 6? Double parity. 2 of these are parity. 2 of these are parity. Because each of these are its own set of RAID 6. Keep that in mind. So because of that, this is 2 terabytes, this is 2 terabytes. 2 terabytes, 2 terabytes. So in total, 4 plus 4 is 8 total. This is different than the answer. I went over this with him in class, so I can confirm it is indeed 8.
Didn't he say there was a typo that I should have said each with 4 readable disks? So technically you'd have 6 disks, 6 disks in total.
Actually, yeah, he went over it another way too, where each had 4 readable disks. So if that was the case, 6 disks are in total on each of these sets. There's going to be 2 for the parity at all times. So now this becomes 2, 4, 6, 8 plus 2, 4, 6, 8 is 16. If that's the case with that. Right? Can anyone confirm?
Yep, that's correct.
Awesome. Yeah, so there's a difference between usable disks, the ones that don't have parity on them and don't have mirrors on them, and like disks in total. So each with 4 readable disks means that it's 4 plus the 2 parity disks. Yeah, no, you're right. He went over it 2 different ways. I was remembering it the way that I did it. But yeah.
Can you explain 5 again? I didn't get it.
Sure, RAID 10? Yeah, totally. So, RAID 10. Inside, out. We have 4 disks total. He's always going to tell us how many disks there are. We have mirroring, and then we have striping, or stripping. It's called striping on the notes, but he says stripping. I don't know. It's the same thing. So what this is saying is that we're going to have 2 groups. We're going to split this into one group, this into one group. Inside group, outside group. Inside is going to have mirroring. Outside is going to be connected with 0. So what this is saying is, inside, you're going to mirror. This is going to be a mirror of this. This is going to be a mirror of this. On the outside, though, you're stripping it. You're stripping it between 2 groups. Your A is going to be here, and your B is going to be here. This is the same as if you had 2 disks, and you put your A here and your B here. It's not like you did A, B on the same disk. So that's what we mean by RAID 10. And this is great because each of these sets have their own mirror, and it's stripped across. So that means I can read both A and B at the same time. So that makes it optimized and also great because if this disk dies, I have this disk. If this one dies, I have this one. So I could have up to 2 disks. Once 2 disks happen, then you're out of luck, but that's what we mean by fault tolerance. Does that make sense?
Yeah, so if this one fails, then it can still operate then, right? Because there's a mirror still.
You got it.
And then the thing is the way the question is worded is confusing. If it's when it says disk 3 fails, does that mean along with disk 1 failing, or is separately, like disk 3 fails separately?
That's a good question. As far as I know, in the answer key, problem set was this again? Oh, there you go. It says the array can still operate normally because disk 2 has an identical mirror of disk 1's, and if disk 3 fails, the array can still operate normally as disk 4 has an identical mirror on disk 3 data.
Oh, okay. So basically, it treated it separately then.
Yeah, and then
Okay.
it also says RAID 10 provides high fault tolerance by mirroring, so the failure of one disk in each mirrored pair does not affect the operation of the array. And the key word here, a failure of one disk in each mirrored pair. Meaning this can fail and this can fail. But once I have two disks that fail in the same pair, then you got an issue. So if the question,
Okay, sounds
yeah, even if they were together, they would be fine because you still have at least one disk of each pair.
okay. So as long as as long as both of them in the same pair don't get corrupted or something, then it's fine.
Yep.
But if it's one disk from different pairs, then it's fine. It'll still run.
Yeah, exactly. You got it.
Okay. Thank you.
Yeah, this is what it says in the answer key, which is good to keep in mind. It says each mirrored pair, a failure in each of the mirrored pairs.
I have a quick question. When it says disk 1 and disk 2 are mirrors, does that mean that 2 is mirroring 1, or is 1 mirroring 2, or is it just vice versa?
It just means they have the same data. If this
okay,
dies,
gotcha.
you still have it here. It doesn't matter which is the mirror. The only thing to keep in mind is that in total you only have one usable disk because one is going to be the mirror. It doesn't matter which one, but whatever you put onto one, you have to make sure is on the other. So you don't have two usable disks. You only have the data of one disk, but it's on two disks as a backup. Does that make sense?
Yes.
Cool. Okay, last problem set. You ready? Were you ready like a whole hour ago for this last one?
I'm so ready to go to sleep.
Ooh. Alright. So let's see. First things first, we got ourselves another disk scheduling question. This is actually like a past exam. This is problem set 14B. Yeah, 14B. It's the second one under RAID, but it has a little bit of everything in it. So this, I'm just gonna go through this really quick. 200 tracks, 0 to 190. Actually, wait, wasn't this the exact one that we did before? I think it was, honestly. Or, no, it was similar. Never mind. Okay. The head is at track 20. And notice how it says moving towards 0. So, for the scan and look, we need to keep that direction in mind. So, we know first come, first serve isn't really listed here. That's kind of self-explanatory. You just do it in order. So we're just skipping that. It's not even in here. Shortest seek time first. So starting at 20, first of all, wow, look at that. We're already at 20. Yay. So 20 minus 20 is 0. Cool. The next closest would be 28. So this would be 8. Okay, and then we'll be moving in the other direction, so 47 minus 28 plus 52 minus 47. Right, that's the next one. Plus 56 minus 52 plus 65 minus, what number was I on? 56. And 69 minus 65. That's a 64. I'm really tired. And 74 minus 69. Add those together. Let me double check that. Yeah, that looks about right. Yeah. Yeah, and just keep that kind of like that. Like, don't solve it because, yeah, we are at our stupidest during exams. We all know that very well. So let's shortest seek time first. Next is scan. So scan, one direction, keep going straight. 20 to 0. Then we go all the way back. So actually I should probably write these guys out. 47, 52, 56, 28, 65, 69, 74. Yeah, so we go through all these. We go back to the 20, and then from 0 we go all the way till the last one is found, which is 74. So that becomes plus 74, right? So we do 20 going back plus 74 going front. Okay, and that would be 94 total. This time for look, we start at 20. Now notice 20 is the smallest value. We don't go any further. We stop at 20. We just have to go all the way far till the final value, 74. So that's actually literally just 74 as that. So at that point, wait, I'm so sorry. I can't do math. We did not go from 0, sorry. 20 to 74. So again, with look, you go from your value to the smallest to the biggest. So we were already at the smallest, we go to the biggest, find the difference between them, 74 minus 20. So that's scan, this is look, and then lastly we've got clook, cscan. So with that, we're at 20. Yeah,
I have a question.
totally. What's up?
Isn't for scan, don't you have to go all the way up to the end, which is 199?
So technically yes, but in this question, you stop when you have no more requests.
Oh, okay.
Yeah, so it's a bit of a trick in that technically, yeah, you go to the end, but it's only asking for these following discs over here.
Oh.
So
Gotcha.
you only go up to that point. So lastly, there's clook and cscan. Cscan, we are going to start from 20. Now we're going to go back to 0, and then we're going to jump to 199 and go back to 28. So 20 to 0 is 20, plus 0 for the jump. We're at 199, and we're going to go all the way back till we get to the next smallest number, which is 28. There's no reason to go to 20 because 28 is the last number. because at that point we finished. So then lastly, we have see look. This time we look, we see 20 is the smallest. There's no need to go to 0. We're going to do our jump here. Jump from 20 to, instead of 199, jump to the largest value, 74. So from 20 to 74, we don't count that. That's 0 for the jump. Plus, we go from 74 to the next smallest, which is 28. And that's literally it. So that's it for that problem.
Wait, so just to confirm, right, for C-scan and C-look, when you're jumping from like 0 to 199 or like, you know, back to the start, we don't include the jump in the head movements, right?
Exactly. Don't count the jump.
Okay.
The jump is always going to be
Okay,
0.
Okay, thanks.
Think of it like a record player. How do you change the track to jump? You pick up the head and you put it somewhere else. Same thing happens here. The only things that we count is when the disc is actually scratching the surface. And that only happens basically any time that we're not jumping.
Okay, sounds good. Thank you.
Cool. Okay, next question. So we get a little bit more RAID now. For each of the following RAID algorithms, find the total capacity. Okay, total capacity and capacity for each. Okay, so RAID level 0, right? This is just the stripping. We have a total of 7 disks. We're able to use all the disks for that because it's RAID level 0. There's no mirroring, there's no parity, there's no backups. So all 7 disks are usable. Now that's bad if one goes down, but we just care about the total storage at this point. 103 times 7. And that would be it for that part. Yes, okay. Then RAID level 5 also has 7 disks, but here's the difference. 4, 5, 6, 7. If this was RAID level 4, 2, 3, and 4 always use 1 disk for parity. But 5 is distributed parity, meaning that A parity is here, B parity is here, C parity, D parity, etc. You get the picture. And now the rest of the data is here too, etc. But if we were to add this all up, right, there's 1 parity per disk. How many disks are there? 7. There's going to be 7 pieces of parity. 1/7 times 7 disks is 1. Therefore, RAID level 5 is also 1 parity. So if there's 1 parity, there's 6 usable data disks. 6 times 103. That's also the same answer for 2, 3, and 4. While we're at it, let's do 6, because that one would be different. That would be 2 parity, and 7 minus 2 is 5 data. Next one, assume a system of 8 disks with 4 terabytes capacity each. 1, 2, 3, 4, 5, 6, 7, 8. So each of these have 4. RAID 0, you can use all of them. 8 times 4. RAID 1 breaks it in half. 1, 2, 3, 4. 1, 2, 3, 4. These are data, these are mirrors. 4 times 4. RAID 5, same reasoning that we had here. When you distribute the parity and you put it back together again, essentially one full disk is going to be a parity. 7 disks will be data. 7 times 4. And while we're at it, 2, 3, 4 function the same way. There would be 7 usable disks, and 6 would be 2 parities. So there would be 8 minus 2 is 6 usable disks for RAID 6. And that would be it for that one. Okay, one more. I think that's actually the last one because the next questions have like page faults in them, and we never went over that. Oh, there's more disk scheduling stuff too. Alright, let's just do this one last one and then call it a night, because at that point the rest of the questions are just disk scheduling, and it kind of is like the same thing over and over and over again. So this time we got 5,000 cylinders, numbered 0 to 499. The drive is currently serving a request at cylinder 143, and the previous request was at cylinder 125. So if we're going from 125 to 143, we know that it's going in the direction to the right. Right, the previous one was smaller and you got bigger, so you went to the right. Likewise, if it said that the previous was like 160 and you went to 143, you know you're going to the left. So this is the order, and it says in FIFO order, so that's first in, first out. So if you had the, I forgot what the one was called, the first, it's getting too late for this, the one that's like first in, first out, it would just literally be in this order. But we're going to be doing shortest seek time first, C-scan, C-look. So shortest seek time first. Oh my gosh, please don't make me do this math right now. Let's just do C-scan and C-look. I can't do math right now. So C-scan and let's do look, scan, look, C-scan, C-look. Jeez. And go from there. So let's see, we got 85, 1465, 920, 1784, 948, 1510, 1025, 1745, and 128. So C-look, I'm sorry, regular scan, we know we're going to the right, and we're starting out at 143. So we're going to handle all of these guys till the end. There's a lot of wasted space. Then we're going to go all the way this way till we get to the smallest value at 85, which is when we stop. So that's going to be 4999 minus 143, which gets you all the way to the front, plus 4999 minus 85, which gets you all the way to the back. So from 143, wait, 143 all the way to 499. Yeah, so that would be about right. Okay, so then we have look. Now look is going to go from 143 to the highest number over here, 1784. Then we're going to go back to the smallest number, which is 85. We add those together, and that's for look. C-scan, we're going to go from 143 all the way to 499. So once again, 4999 minus 143. Then we're going to jump all the way to 0. Jumps don't count. And then we're going to go from 0 to the next highest number, which is, the last number, which is 128. That would be C-scan. So again, we go from 143 to the end, do a jump, 0 to the last term. And lastly, to the last part of the thing, see look. Go here, we stop short at the last term, 1784. This is where we do our jump now. We don't go to 0, we go to the smallest value, 85. Again, don't count the jump. And then we do 85 to the last value, 128. And that is C-look. And that marks the end. Any questions?
I have a quick question. So I know in the first question of the practice exam, right, for scan, we did not go all the way to the end, right? But for this part for scan, we did. So what is like the keyword like to look for in the question?
Are you saying that I went all the way to the last term here, but on the other one, I went, wait,
It's just, yeah.
I think what you mean is because it's the direction in which we're going. So,
Okay.
yeah, if we're going to the right, I'm going to go all the way to the end, and then I'm going to go all the way backwards, but I'm going to stop short before I get to the 0, because this is the last request that I need to get. In this case, my last request was 85. The other question we did, which kind of was like a little bit more backwards, where we went to the left, we went all the way to 0, we went all the way back, and we stopped here instead of here, because this was the last request. So it just matters where the last request is.
Okay, thank you. Thank you for doing this review session also, I hope all of us on the call get 100. I think we all need it.
Absolutely. I wish everyone the best. We all need it.
Yeah, same.
Thank you.
Yeah, thank you, Lauren.
Yeah.
This review helped a lot,
Yeah, I'm glad it
especially
did.
the messy part.
Thank you for your time.
Yeah, no problem. All right.
Thank you, Professor Lauren. That was really great. Thank you so much. Appreciate it. Best of luck, guys, for tomorrow.
Good luck, guys. Get some rest.
Well,